this. Good morning. All right, let's do it. So just some quick review from last day. It was just on Wednesday. So, but we did introduce some important concepts, right? So we introduced the limit definition of the derivative, the limit definition of the derivative. But then I also said, okay, we're not going to be using the limit definition for the rest of the course. That's going to be crazy, you'll see. But it will always work, but sometimes it'll just kind of blow up, and I'll show you some examples in the next section. But so the limit definition of the derivative says that the derivative of f of x is the limit as h goes to 0 of f of x plus h minus f of x over h. And what we've found, right, is that we have to manipulate this, this function on its own until the h kind of cancels out or disappears or doesn't go to 0 anymore, right? So we don't have the denominator going to 0. And so I'll throw a little highlight around here because the limit definition of the derivative is really important. And then we use that, and we found the derivative of x to the 3 minus x. But before I mention that, I do want to also re-emphasize the different notations that we can use, right? So probably the easiest notation is this prime notation to denote the derivative. We can also use, and the name escapes me, differentiation operators, or I would call them differential operators, but I guess it's differentiation. And remember, differentiation is just taking the derivative. So those we use interchangeably, but also I want to just bring in this so that we can have it and notice that these all mean the same thing. These all mean the same thing, right? So for a lot of the examples that we're going to use, we'll do stuff like d dx of f of x. So not necessarily the prime notation, although sometimes if I'm in a rush, I'll use the prime notation. But being able to read all these as equivalent statements, that's going to be important. And then we also introduced higher derivatives, right? So I can take the derivative of the derivative, which if we kind of think about it, so the derivative is the slope of the tangent line. So that's the rate of change of the original function at that point of x. Now, if I take the slope of the tangent line, and what I mean by that is the rate of change of the tangent line, right? So how quickly is the tangent line changing? Because the tangent line is also going to be a function, right? Then I'm taking a higher derivative. So we can take the derivative of a derivative, and then we can take the derivative of that, and we can go on for as long as we want. At some point, it's going to go to 0, which we'll see in our examples when we finish them off here. But I do want to bring in kind of these higher derivatives, how we denote them. So we can take higher derivatives like so, right? So I'm taking d dx, which is a very common notation for saying I'm taking the derivative. So I'll take the derivative of dy dx. That's really d dx of y, right? And so take the derivative of y with respect to x. Okay, and then so I'm taking the derivative of the first derivative, which I can rewrite as d squared. And if you just multiply across here, right, then you get d squared sort of well, you get d squared y, but then here it gets a little bit weird because now the x is squared. So it's not really multiplying, but that's how my mind works. When I read this, okay, I know this is the second derivative, right? And so the fourth derivative we would denote by d to the fourth, oh, maybe even make it look like a 4 of y dx to the fourth, right? And so on and so forth. You can take the 27th derivative if you wanted to, right? I would, if I had to do that, I would probably use maple, but yeah. You can usually, if they're asking you to find things like crazy things like the 27th derivative, you can usually find a pattern, and we'll see that more when we introduce trig functions, but it's not something that I want you to focus on, so I shouldn't have said anything. So what we found is we used the limit definition of the derivative to find if f of x, so we had this go-to function x to the 3 minus x, right? Then what we found, just to recap, because we'll use it here, the derivative of f of x we found was 3x squared minus 1. And let me just bring that up here, 3x squared minus 1. I can't remember how far we got. Did we find the second derivative? Let me grab it here. We did. Okay, so here, right, so let it catch up. Okay, so we found that the derivative is 3x squared minus 1, the first derivative, and then we took the derivative of that, blah, 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 blah. I kind of cut to the chase here, of simplification going on, but that's just math, right? So we're okay with that. And then our limit became 6x. So then our second derivative was just 6x. So let's just remind ourselves here. And f double prime of x, which is the second derivative, became 6x. And then we had a look at the graphs of the three of these, so f of x, f prime, and f double prime of x. And with a little bit of patience, you can kind of tease it apart and say, okay, well, when the slope is positive of the original function, and let me just go grab it here. Copy. Right, so then we said, okay, I've got this original function f, which we know if it's x to the power of 3 is the highest power, so it's a degree 3, then I'm expecting this type of behavior, right? And so this is my f, and then we said, okay, well, the derivative becomes a quadratic, right? And in fact, it becomes this sort of quadratic here. And so what we said was, okay, well, we have to remember that at the maximums and minimums, we have a slope of 0, right? And so we said, well, we're going to use that in order to map out our derivatives, right? So at maximums and minimums, we have a slope of 0. So that's where it's going to cross the x-axis, right? So here, wow, doesn't really look like it, does it? Guess I wanted it to be at the somewhere around here. In fact, where it crosses the x-axis, that's where the slope of the tangent line of the original function is 0, right? And then same thing here. Maybe I'll just work backwards, right? We said, okay, I've got another derivative that has to be 0, so that's where it crosses the x-axis. And then we talked about, okay, so here I have positive slope on the original function, which means I have to be above the x-axis for my derivative. And then here I've got a negative slope, so here I've got a negative values on the derivative. And then here we get a positive slope again. And so we can do the same thing, but now trading in our original function for our first derivative and comparing it to the second derivative. What we said too was, okay, if I start with an x to the power of 3 function, my derivative of that is going to be, at least in my mind, I think of it as simpler, right? So an x to the power of 2 function. So the next step simpler from x to the power of 2 is just x, right, which is a straight line. So the second derivative becomes a linear function. So let's see here. What did I want to say here? So that's the end of what we were talking about last day. I will say that we can interpret the second derivative, right? If you think about it, it gets a little bit dicey when you have to kind of articulate it, because it's the slope of the tangent line of the tangent line of the original function, right? So we can interpret f double prime of x as the slope of the curve y equals f prime of x, right, the derivative, at some point x, f prime of x, right? Remember, we're just swapping out the original function for the derivative if we're talking about the second derivative. Okay. So in other words, it is the rate of change, right? So remember, the derivative, it's the slope of the tangent line, but it's also the instantaneous rate of change, right? Depending on what the scenario is, it might be more helpful to think of it that way. So it is the rate of change of the slope of the original curve. Y equals f of x. So for that last example, we're asked to find the third derivative and the fourth derivative. So let's go nab it here. So again, we're using the same function. And so now we have to find the third derivative and then the fourth derivative. So we can use the limit definition. I'm going to skip it actually, because we've got funner things to do today. So you absolutely can use the limit definition of the derivative, but from the second derivative of f, which was 6x, right, we see that this is a linear function. And so thinking back to our pre-calc days, a linear function, well, it has a constant rate of change of the slope, right? And which makes sense if you've got a straight line, right? So, so we know the second derivative is a linear function with a slope of 6. So therefore, right, the rate of change is constant at 6. Therefore, the rate of change, which is the derivative, the rate of change is constant at 6. Of course, we can confirm using the limit definition of the derivative. I'll say we could confirm this using the limit definition. But how about you just take my word for it? And I think it feels pretty reasonable. So if we think about, okay, so then what we're saying is that the third derivative is just going to be 6. If we think about 6 as a function itself, well, that's just y equals 6. It actually doesn't care what x you put in there. It's just always going to be 6. So if you think about a straight horizontal line at 6, well, now there is no slope, right? The slope is 0. So here, if you just think about so then the slope equals 0. So now, what can we say about the derivative of the third derivative, which is fourth derivative? So the fourth derivative, which we start using these little brackets around, because I mean, having all these primes, we kind of cap out at 3. And so after that, we use just brackets around the derivative that you want. So the fourth derivative is 0, right? Since the slope is 0 of a constant. Here, the rate of change, right? And especially if you kind of spell it out this way, the rate of change of a constant function, well, a constant function isn't changing. So the rate of change of a constant function, is 0. Okay. Which we could confirm using the limit definition of the derivative, but what do you say we leave it behind? All right. So that's the end of chapter 2. End of chapter 2. Oh, I wanted to ask you guys, do you want me to extend the quiz deadline till Sunday, or do you want me to keep it tonight?
I'm gonna be real, it's probably better to keep it like this, or I'll just give myself more excuses and not just like put it off.
Not do it. Okay. How about you, Carly? Do you have a preference? Let's see. I'll just do a reminder. Quiz number 4, I think it is, due tonight. Awesome. Yeah, it might be nice to get it done before the weekend, but if you do find that you want me to extend it, just let me know and I can extend it. That's fine. But yeah, I know you guys are so good. I'd be like, Sunday, please, and then put it off till Sunday night. Yeah, so just let me know and totally fine. Okay, let's do it. Let us finally start chapter 3. What I'm finding with chapter 3 is it's kind of unfair because we're going to introduce all these rules for finding derivatives depending on what type of function we have. And then it doesn't really take that long to introduce these rules. And so it feels like it's just a blip, but then I expect you to know them for the rest of the course. So of course we're gonna work through lots of examples and stuff, but yeah, it doesn't get a lot of screen time for how important it is for all these rules. So that's a little bit disproportionate, but we'll just work through them. And sometimes what you'll find is that we introduce the rules and then we don't really focus on working on them until we've introduced a couple more rules, especially in 3.2, I want to say. But so chapter 3 in general is just called Differentiation Rules. So as promised, right, we're not going to do the limit definition of the derivative forever. In fact, it kind of ends now. I make you do it on the quiz for sure and on the next test for sure, but we'll have easier ways of finding the derivative. So 3.1 is on the most basic derivatives of polynomials and exponential functions. So in general, what I've decided to do is I'm not going to do any proof. A lot of these proofs are outlined in the textbook, but for us, if you just accept it as fact and use them and apply them, these rules, then I'm happy. Okay, so I'm not going to go through and prove them, but we could go through and use the limit definition of the derivative to prove all these things. So I do want to say that we can always use the limit definition of the derivative, but sometimes or often it's a little bit tricky. So we can always use the limit definition of the derivative. Definition of the derivative to find the derivative. And just as a reminder, f1 of x is, oops, forgot the limit. The limit as h goes to 0 of f of x plus h minus f of x over h. Of course, that will always work, okay? But however, to avoid taking the limits all the time, or I guess it's just one limit, all the time, differentiation rules have been established, and that's what we're introducing today. Differentiation rules have been established. Yeah. And I posted some notes, I feel like it was maybe yesterday. At the end of section 3.2 notes, so the section 3.2 notes, at the very end, if you're just going to scroll to the end, all the differentiation formulas are summarized here. So we're going to go through them one by one and kind of pick away at them. But if you're looking for kind of a summary table, this is the one that I would use, right? Or copy out or definitely have ready somewhere. And so they're all summarized at the end of 3.2 notes. Okay. So here, I'll just say summarized at the end of the 3.2 notes. Okay, just as a heads up, because otherwise it can feel like, oh, there's all these rules and they're everywhere, and then, but don't worry, they're all kind of kept together there. Okay, so a lot of these are proven using the limit definition in the textbook. So many of the differentiation rules are proven, right? And I'm not focusing too much on proofs, but just in case it comes up. So many of the differentiation rules are proven using the limit definition, and that's how you would do it in the textbook. Yeah. We will state them here and just accept them as fact. So we will state them here and accept them as fact. If we were hardcore mathematicians, we would say, no, I need to see the proof first, and then I'll accept it as fact. But hopefully you guys are okay with just taking it as fact. Accepting them and accept them as fact. First one is, and you'll notice that, so we're in the 3.1 notes here. Okay, the first one is actually exactly what we just established, right? And we did argue that, okay, so a constant has a slope of 0, and that's going to be true always, right? It doesn't matter what horizontal line you have, the slope of that thing will always be 0. So the derivative of a constant, and notice that we use the d dx notation, so the derivative of a constant is 0, right? So we can bring that in here. Hopefully everyone's on board with that, right? So here, the derivative of a constant will always be 0. Okay. So the derivative of a constant is 0, which is what we were just talking about. Right? We kind of argued, okay, well, there's no change here, so 0. How about if you take the derivative of x, so think about the line y equals x here. Well, y equals x, and I've got the graph here. So y equals x, that's a slope of 1, so it's a straight line with a slope of 1 and a y-intercept at 0, right? And so I know that the slope of this thing is 1, and so the derivative of x with respect to x is 1. Okay. So that's another one we can just accept as true, right? And then the third one I want you to accept as true for now is the power rule. So the power rule says that if you have x to the power of n and you want to take the derivative of x to the power of n, what we do is, and in my mind, what I do is I just kind of bump it from the right. And what happens is that this n falls down in front, right? So now you've got n times x. And then you have to subtract 1 from the power, so to the power of n minus 1. So that one's a little bit trickier, right? But as long as you remember that, then we can just go ahead and use it, right? And so here, if I just kind of rewrite this here, d dx of x to the power of n. So I just imagine, so here I've got my x, to the power of n gets kind of bumped down in front, and then I have to subtract 1. So there are scenarios where we might want to rewrite x, right? Especially things like the root of x. You can rewrite as x to the power of 1 over n if you've got the nth root. And I think I've got some examples in there. So just remember, and this is kind of the new weird thing, right, is that, okay, if I have x to the power of something and I want to find the derivative of it, right, then this n kind of falls down in front, and then I have to subtract 1, right, from the numerator or from the power. So, and that's true for any real number. So n can be negative, right? You still have to subtract 1, and we'll see a couple of examples. But so that one's going to be really important. Okay. And once you've kind of done a few, that's like, oh, okay, I see. What did we say earlier, right? We said, okay, if I start with an x to the power of 3 function, then the derivative of that becomes an x to the power of 2 function. And that's exactly what's going on here, right? If n was 3 initially, then I end up with the derivative being to the power of 2, right? The highest power of 2. So, so we've already seen this in action. It's just now here it is on paper, and this is what we'll use. So they had a couple of examples here. They just worked through it. Right? But if we have x to the power of 6, right, then I can kind of just give it a bump. I give it a bump from the right, and then the 6 falls down in front, and then the power decreases by 1 to be 5. So 6x to the power of 5. Same thing, x to the power of 1,000. Well, it becomes 1,000 times x to the power of 999, right? Same idea. T to the power of 4. Now, if t is the variable, then I'm assuming I'm going to be taking the derivative with respect to t. So even though we've been talking about x's before, right? And you would probably just do this anyways, right? You would probably just say, okay, well then I need to decrease, I need to bump that 4 down in front and then decrease the power of t by 1, which is exactly what you're doing. But notice that this is changing here, right? dt, if the variable here is t, and that's all that's saying, right? Same thing with dr, right? If you have, and it is showcasing a couple of different ways that you can write things, right? And so if you have function y equals t to the 4, then you could say dy dt, which is just saying the derivative of y with respect to t is this, or you can say d dr, right? So the derivative with respect to r of r to the power of 3 becomes 3r squared, right? So once you have the hang of that bumping down, oh, say that again.
Had some fun with that on the lab on Tuesday, where it's like,
oh,
hey,
really?
this isn't working right. This isn't working right. Oh wait, I put it in as like f of x when it's actually like g of t. Anyway.
Yeah, it doesn't like that. Yeah, so you want to keep track of your variables, but the behavior is always the same, right? So don't let it throw you off, but it is important, as Maple will show you. So let's do a couple of these examples on our own, I guess. So if I want to differentiate something like 1 over x squared, like I said before, right, we might need to rewrite this as x to the power of something, right? 1 over x squared, I know I can rewrite as x to the negative 2, right? And so here in a, f of x, I can rewrite 1 over x squared is really just x to the negative 2. So just you remember those exponent laws of how you can rewrite exponents and how we simplify exponents. Might have been a while since we talked about it, so might need a refresher, but just how do we rewrite exponents, right? So then if I take the derivative of f now, and I'll try to use some fancy notation, d dx, for example, d dx of f of x, although honestly, often I'll just default to the prime notation. Oh, if there was a variable, so if you had something like, do you mean like 2 over x squared? This would be the same as 2x to the negative 2. Or even if you had t over x squared, that becomes t x to the negative 2. Awesome. Yeah, so you can just kind of bring it up to the same playing field by negating that power. So if I want to take the derivative of f of x with respect to x, then, okay, so now my power, remember, so what I do is I bump down the power. So that's like the entire thing, right? Negative 2 has to bump down in front. And so this becomes negative 2 times x to the negative 2, and then I subtract 1. So often we'll need to kind of simplify these things, especially if I'm dealing with negative powers. But so this becomes negative 2x to the negative 3. But kind of the same way that we brought the x upstairs, we can simplify it and bring it downstairs again by writing, well, this is the same as negative 2 over x to the 3. So unless the negative 2 is also to the power of negative 3, it would stay up top. Right? That can be a little sneaky. Okay. How about B? So even if we have roots, right, remember the third root is the same as whatever is inside to the power of 1 over 3. But then again, kind of drawing on our exponent laws, if x is squared inside, we can rewrite this as x to the power of 2 over 3. Right? So B, if I have, what was it? Y equals the third root of x squared. First thing I want to do is I'll want to rewrite it as just the power. And so this becomes x to the 2 over 3. Fractions. No one likes fractions, myself included. So, but that's okay. We have to deal with fractions, right? And so if I take the derivative of this thing, then I'm doing dy dx or d dx of y, or lots of different ways that we can write it, as you know. That's going to be the same as I'm just seeing if I want to rewrite it. No. Right, I have to bump that. So I just give it a bump. 2 over 3 falls down in front. So it's always the entire power that falls down in front. And then you have x to the 2 over 3, but then minus 1, right? Remembering how to subtract fractions, well, I need to have a common denominator, so I have to rewrite 1 as 3 over 3. So then I have 2 minus 3, negative 1, over a common denominator of 3, which I will write out here. I'll just show it here that I'm multiplying by 3 over 3 to force that common denominator. So then I get 2 over 3 times x to the 2 minus 3 over 3. You can skip that step if you wanted to go straight to negative over 3, but I just want to show, because it has been a while since we have dealt with fractions. So 2/3 x to the -1/3. This is the same, right? You could probably just leave it here, that's fine, right? So maybe what I'll do is this is the same as, because here you're done, this is it. But if you wanted to rewrite it, this is the same as 2/3 times the third root of x, right? X to the -1/3 is the 1/3 root of x. Okay, so that's a good one to know, right? X to the power of something, if I take the derivative, just bump it down, move on. So if you think about a polynomial, right, that would be our natural next step here. We could have something, right, if you think about a quadratic, ax² plus bx plus c, then I've got these constants out in front. And so we're building up to be able to deal with polynomials. So now we have the constant multiple rule. Constant multiple rule, I don't want the whole thing. If you think about a constant times f of x, remembering that that constant doesn't actually care about x, and remembering that we're differentiating with respect to x. So what happens is this derivative just kind of attaches to whatever has an x in it, right? And so we can bump this constant outside. Unlike the derivative of just the constant, right, which is 0, if it's attached to some x, then it just kind of, so again, in my mind, and you'll have to develop your own ways of kind of memorizing these things and kind of having them available, right? And so in my mind, the derivative just kind of attaches to whatever the x's are, right? And so it kind of scoots out the constants, and the constants we just multiply by whatever the derivative is, right? And so constants can be moved outside of the derivative, or constants move outside of the derivative. The derivative only cares about x. How is x changing, right, or with respect to x? So, got another example here. Oops. And maybe I should grab them both while I'm here. So kind of no surprise here, but if you have 3 times x to the power of 4, what happens is the derivative, if we want to take the derivative, we can kind of just hold the 3 outside and then take the derivative of x to the power of 4. Same thing with the negative. Negative x is really just -1 times x, right? So here I've got a constant of -1, which I can kind of push to the outside and figure out what the derivative of x is. And then I'll have the overall derivative. So here for a, if I want to find the d dx of 3x to the 4th, this is the same as 3 times the derivative d dx of x to the 4th, which is exactly what we just learned how to deal with, right? And it behaves just the same way that you think it will, right? When I bump this 4 downstairs, kind of down in front, I guess, it's going to multiply that 3, right? So it becomes 3 times x to the power of 3. So this becomes 3 times 4x to the power of 3, right? Bump that 4 down in front and then decrease the power by 1. So then I get 4x to the power of 3. Which, if we multiply this out, puts us at 12x to the power of 3. Let's do the same thing for b, right? But just remembering that the negative is actually -1 times x makes it a lot easier. So I'm just going to do it over here. Let's move these over just a smidge. So I'm on the same page. So I want to find d dx of -x, which we'll just remember is -1. If you don't want to put the 1, that's fine. I usually just pull out the negative. I don't do the 1, but technically it's there. d dx of x, which we actually had as a fact that the derivative of just x is just 1, right? Also, if you think about x as a power, well, that's x to the power of 1. Right, and so we could actually just forego that first or the first couple of facts where if we have x to the power of 1, well, then the derivative is 1. So here, right, this becomes, so this is d dx of x to the power of 1, which is 1 times x to the 1 minus 1. Anything to the power of 0 is just 1. Which is 1 times 1, which is 1. Right? And so overall, this becomes -1 times 1, which is just -1. So you could skip that fact and just develop that the derivative of just x is just 1 from the fact that x can be written as x to the power of 1. And then just move that 1 front and then decrease the power by 1. Same thing for a constant, right? A constant is something times x to the power of 0, right? 6 as a constant is 6 times x to the power of 0, but then I move that 0 out front and that's why it becomes 0, right? So we could actually skip those first two facts that we started with and only have the power rule and the constant multiple rule. Okay, good. So, all right, we've got kind of some groundwork done here. And so now if I start stringing these together, thinking about polynomials in specifically, in particular or specifically, so if I start stringing these together with addition and subtraction, well, they have their own rules, but they behave the same. So here, and what's nice about addition and subtraction is that it just transfers through. Okay, so here, if I want to take, so assuming that f and g are both differentiable, right, that's going to be a key, right? And we looked at some different areas where we would not be able to differentiate, right? Especially if you have a cusp or a vertical tangent line or kind of a jump discontinuity or something like that, right? So assuming that f and g are both differentiable, then if we're adding, or look, just kind of make the connection here. I know it's really wordy with the ddx's, but I'll summarize with prime notation. How about then if I'm adding two functions together and they're both differentiable, then what I can do is I can just add the derivatives together. Okay? So that's going to help us find derivatives of polynomials, of course. And so here, these two in prime notation And I'm going to do plus minus because if you kind of do a little deep dive here, these are the exact same, except now I'm subtracting or adding. So they behave the same way regardless. So in prime notation, what do we have? We have, well, if I want to do f plus or minus g, and I want to take the derivative of that, right? And this extends to more than two functions, but we'll focus on two. Well, that becomes the derivative of f plus minus as appropriate, plus minus the derivative of g, right? So the derivative just kind of translates inside, essentially. Okay, so we will use this. We will use this for polynomials. Okay, so nice. As long as we're adding, subtracting functions, I can just take the derivatives as I move along, and then I have the derivative, right? So let's do example. Let's do this example. Okay. First, I want you to be really grateful that you don't have to use the limit definition of the derivative. F of x plus h minus f of x over h. That's a no for me. Right? X plus h to the power of 8. You'd have to expand that all out and then do plus 12 times x plus h to the power of 5. You'd have to expand all that out. It would take you half a day. It sounds terrible. So first, imagine using the limit definition of the derivative. Flat face. And we're obviously not going to do that. We've moved past that. You could, but like I said, expansion alone would take you quite some time, I suspect. At least me. So now what I'm going to do is I'm going to think about this as, so these are just individual functions being linked together with addition and subtraction. Sometimes we have constants out in front, but we know how to deal with that. And so this derivative actually becomes really easy to work with, right? So derivatives of polynomials are just so fun. So if I want to take the derivative of this thing, and I'm not going to write it out again because I'm worried I'm going to run out of space. So here, I'm just going to say that this becomes, and I'm going to use my whole page just in case. So if you wanted to just work it out, I don't really expect you to need more than 2 or 3 lines for this. We are going to take it nice and slow for these first few times. And then as we kind of move through the course, I probably just expect to see the answer on the next line, right? I don't need to see all the activity, right? And so technically what we're doing is we're saying, okay, well, so I'm doing lots more steps than you have to. But this becomes d dx of x to the power of 8 plus d dx of 12x to the 5 minus d dx of 4x to the 4 plus d dx of 10x to the 3 minus d dx of 6x plus d dx of 5. And this is by the sum and the difference rules. So I'll make a note of that here. That's how I was able to do that. By the sum, and difference rules. Next thing I'm going to do is I'm going to bump those constants outside. So I'm just doing these really, really nice and slow. Painfully slow, some might say. So the first one doesn't have a constant, so I'm just going to rewrite d dx x to the power of 8 plus 12 d dx. Remember that d dx, the derivative with respect to x, of course, just clings to whatever x's there are. So 12 x to the power of 5 minus 4 d dx x to the 4 plus 10 d dx x to the 3 minus 6 d dx of x. Should I just do it? 0? Zero that out. Most because I'm running out of space. Well, I guess I shouldn't. I kept all the other d dx's. Do it on the next line. So this is by the constant multiple law, or what's it called? Is it a law? Rule, probably. Constant multiple rule. Okay. Now I'm going to use the power rule to just bring these powers down, remembering to decrease each power by 1. No, you can just give the answer. Because it's our first polynomial, I wanted to outline it. I'm never doing this again, by the way. Yeah. But yeah, I have a hard time just kind of skipping through stuff. So that's why I'm, here we go. We're going to do it nice and slow. And then I'm never doing it again. Then I'll just assume that you can take the derivative of polynomial. Yeah, don't worry. This becomes 8x to the 7 plus 12 times 5x to the 4 minus 4 times 4x to the 3 plus 10 times 3x squared minus 6 times 1 plus 0. Or if you wanted to, and I'm just going to keep it on the same page here. I've got a page break right there. Expanding this out, right? 12 times 5 is 60, 4 times 4 is 16, and 10 times 3 is 30. So I get 8x to the 7 plus, oops, I almost skipped it again, 60x to the 4 minus 16x to the 3 plus 30x squared minus 6. Done and dusted. Noticing, right, that the power has decreased by 1, which is the what we found earlier, right? Just for fun, right, we found the derivative of x to the power of 3 minus x, right, before. How easy is that if you just have the power rule and knowing that it's a polynomial, right? And so recall from 2.8, right, we had f of x was x to the 3 minus x, and then we did all that work and we found that, well, f prime of x was 3x squared minus 1, right? I can take the derivative of that, right? Second derivative here. Again, I bump that 2 down in front, so now I get 6x minus 0 is just 6x. Take the derivative of 6x. Well, now I'm just left with exactly what was going on over here, right? 6x. So the third derivative becomes just 6, right? Confirming exactly what we found in the previous section, but probably 50 times faster. And then, of course, the fourth derivative was 0. Right. So just the polynomial, we can easily just kind of plow through it. Takes practice, right? But you will be really fast at working through polynomials. And maybe you already are. So let's do another example here. A little bit funner example, because we have to do a little bit more thinking, right? We'll find the points on the curve x to the 4 minus 6x squared plus 4 where the tangent line is horizontal. Now we've already talked about this, and it's going to be really important to remember the tangent line is horizontal at maximums and minimums, right? And so the tangent line is horizontal at maximums and minimums. In fact, the maximums and minimums are going to be really important in fields like optimization, right? If you want to optimize some sort of procedure, right, then you are either working at a maximum or a minimum, depending on, the angle that you're taking. If you want to maximize profit, for example, of course, that's where the tangent line is horizontal, but at the top, right? And if you want to minimize costs, for example, sorry, a lot of mine are kind of business examples, but it applies to lots of different fields. But if you want to minimize costs or time or whatever, then of course the horizontal tangent line is at play again, but you have to figure out where their maximums and minimums. So where does this thing have maximums and minimums? Well, I can find horizontal tangent lines, right? If I can have the derivative, so if I have the derivative, then I have an equation for the tangent line. And if I force it to be 0, then I have horizontal tangent lines. So at maximums and minimums, horizontal tangent lines mean that the derivative is equal to 0. So what we'll do, and this is a pretty common question that we ask in this course, right, especially because it's so important to be able to optimize things. So kind of getting used to this type of problem is a good idea. Where is this tangent line horizontal? Well, it implies that you know that a horizontal tangent line is a slope of 0, right? So you have to first find the derivative and then set it equal to 0, and then find the values of x that make that happen. So let's see here. I'm not going to graph it in Desmos because it'll kind of give it away. Oh, I guess I should switch to my normal color here. But this graph, because it'll give us the maximums and the minimums, so I don't want to do that quite yet. But this graph basically ends up looking like a W. And so here, here, and here, I guess I gave it away that it's on the y-axis, but we'll solve for it anyways. So we're going to have 3 horizontal tangent lines, right? So that's what we're expecting. So what I can find is that if I have this function, let's just use prime notation, get a little lazy. Y prime is going to be 4x to the 3 minus 6 times 2 is 12x plus 0. Are you guys okay if I just go straight to it? I wasn't even going to write the 0. Right, but this becomes 4x to the 3 minus 12x. I can write it out more thoroughly, but I've taken the derivative of this polynomial down here. So now what I want is I want to find, okay, so this is the slope of the tangent line at any value of x. So this is the function for the tangent line at any value of x. The function for the tangent line, sorry, for the slope of the tangent line at any value of x. When I say tangent line, often in my mind, I mean the slope of the tangent line, but say what you mean, not what you, yeah. So what I want to do is I want to force this slope to be 0. So we need to solve for the values of x that yield y prime is equal to 0. So replacing y prime with what we just found, right, 4x to the 3 minus 12x equals 0. Now I'm just back to normal math, right? I have to factor this thing. Where does it equal 0? So what I see is I can factor out a common multiple of 4x. So I'm going to extract that to the outside. So I get 4x times x squared minus 3 equals 0. So now, well, this is going to be 0 if 4x is 0, but the only way that can happen is if x is 0. So this is 0 if x equals 0. And this is 0 if x squared minus 3 equals 0. Well, x squared minus 3 is 0 if x squared is equal to 3. But remembering when we take the square root, I need to kind of reintroduce the negative version. So then I have x is the plus minus root of 3. So then we have horizontal tangent lines, and like we expected, we found 3 different values of x. And if we had graphed it before in Desmos, we would have seen that graph. Okay, I'm expecting 3 different values. And so now, right, at x equals 0 and plus and minus root of 3, you could plug these back into the original function to figure out what these points are. So what we'll say here, therefore, the given curve has horizontal tangents when x is, and I'll do them in order, 4x to the 3 minus 13x. I would still extract a common x to the outside, so then you'd have x times 4x squared minus 13, and then you'd have a very similar situation, right, if you've got an x in both. So in order, yeah, so you don't have to have the 4x. You can just, if you have x to the power of 3 and x, you can always pull out an x. And then whenever you have an x on the outside, well, this whole thing is going to go to 0 if it's being multiplied by 0. Awesome. Nice. So in order, if x is negative root 3, 0, or the positive root 3, that's when we have horizontal tangents. So we could find the points by evaluating the original function, right? So if I go here and I put in the original function, which was x to the power of 4. Hey, why did it do that? I hit the wrong button. X to the power of 4, step it down, minus 6x squared plus 4. So here we could have just grabbed the answers, and of course negative 1.732 is the approximation of the negative root of 3. You could have grabbed it from here, of course, but I need to see the work with finding the derivative and stuff like that anyways. So, but it's always nice to be able to check your work, right? Oh man, time flies when you're having fun, huh? Give you the choice. Do you want to break now, or do you want to end a little bit early? I can go either way.
Ending early. He sounds nice. It's because, quite frankly,
did you say ending early?
Ending early.
Let's end a little bit early then. How about that? Okay. Yeah. You got it. It's Friday. Let's do it. Okay. We got this. So, so you could grab the points here, or if you evaluated the original function, x to the 4 minus 6x squared plus 4, you would find that the y values here are at negative 5 and positive 4. Okay, but I'll keep that off the page because there was a page break there, so slave to these page breaks. All right. Well, actually, okay, never mind. I'll write it down. So we could evaluate the original function only because I know from teaching these Maple labs, I don't have any this term, but I know from teaching the Maple labs that this can be a confusing thing. So if you find these values of x and you want to find at what points do these have horizontal tangent lines, then a lot of people want to put it back into the derivative, but that's not true. It goes into the original function. So I guess I should mention it. So we could evaluate the original y, and maybe I'll say y equals whatever it was, x to the 4 minus 6x squared plus 4 at x equals negative root 3, 0, and positive root 3 to find the points where the tangent line is horizontal and they're going to be negative root 3, negative 5, 0, 4, and positive root 3, negative 5. Okay, great. We have, I feel, mastered differentiating polynomial functions. So bring on all the polynomial functions. They're really not that bad with all these rules that we've introduced. So the last thing in this section is the exponential function. We're going to focus on e to the x, which is the exponential function with the Euler constant e. We'll talk about the behavior of other functions, right? Other exponential functions later, but this one is special. We'll talk about e to the x because it is really special. So exponential function, and we'll talk about why it's special. Exponential functions. So we'll talk about the number e, right, which is Euler constant. Euler was which is spelled like Euler, but you actually say Euler. He's a mathematician, or he was a mathematician. He's long gone. Very similar to pi, it's an irrational number, so it keeps going forever and ever. It just doesn't have the same publicity as pi for some reason. So e is roughly 2.7182818. Keeps going forever. So roughly 2.7, 2.72, some people maybe round to. If I had to use a rounded value, which you don't, it's on your calculator, I would use 2.7182818. There's a song, I don't know the song, I have never known the song, but my master's supervisor would always sing the song. So it's like 2.7182818. Anyways, pretty stupid. You don't need to know e to however many decimal places. All right, so by definition, okay, the reason e is so special is because it comes from this limit definition. So e is the number, so that, and this kind of notation should look pretty familiar, right? Is the number so that the limit as h goes to 0 of e to the power of h minus 1 over h, it becomes 1, meaning that the derivative of e is just 1, which, yeah, so let's just kind of talk about what this means. So this means of all the possible exponential functions, right? B to the power of x. So of all the possible exponential functions, which have the form y equals b to the x, right? That's an exponential function when the x is in the power. But in this section, we're focusing on e to the x. The function f of x equals e to the power of x is the one whose tangent at 0, 1. So remember, the graph of e to the x, it goes through the y-axis at 0, 1. Okay. And what this is saying is that, okay, well, at 0, 1, the slope is also 1. Okay. And that's kind of a special property, and that's why we like e to the x so much. So the function f of x equals e to the x is the one whose tangent at 0, 1, right? When x is 0, ex is 1, right? Anything to the power of 0 is 1. So e to the x is the one who's tangent at 0, 1, or just when x equals 0, if you prefer, right? You don't have to talk about just the point, but when x is 0, has a slope of 1, has a slope, which, remember, f prime at 0 is the slope at x equals 0, that is exactly 1. Okay. So what that means is that the slope of the tangent line is equal to the y value of the function itself, right? And that actually is true for all the values. So let's just grab this one here, copy. It's lagging on my end here. So here, right, what we're saying is that, and of course, it's going to be really useful to remember what the graph of e to the x looks like, especially that it crosses the y-axis at 0, 1, right? And so here, when x is 0 and y is 1, the slope of this thing is also 1, right? And then what we'll see in general, or what we'll establish in general, is that when at any value of x, the slope is e to the x, which is the y value. So it has that kind of special property of the slope of the tangent line is the same as the y value that it's at. Okay. So, well, the slope of the tangent line sounds familiar. That is the derivative, right? So here, what we've established, right, if the slope of the tangent line is equal to the y value at that point of x, well, if y is equal to e to the x, then the derivative of e to the x is just e to the x, right? And so that makes it really easy to deal with. So here, what we're saying is that the slope of the tangent line, to the curve y equals e to the x is equal to the y coordinate of the point. Okay. So as long as you kind of lock e to the x down, okay, I know how to find the derivative of e to the x, it's just itself, right? Then we can do things like, whoops, like example 8. Remembering that e to the x is just a function itself, right? So even though we don't have a polynomial anymore, I'm just subtracting two functions, right? So I can take the derivative of the first one minus the derivative of the second one. And we're going to find f prime and f double prime. So we're going to take a couple of the derivatives over. So here, this becomes, I think about f prime of x, and just to get in the habit of using the d dx, this is the same as d dx of e to the x minus d dx of x. You don't have to show that. If you wanted to skip straight to e to the x minus 1 at this point, that's totally fine. I just wanted to show that, well, we're able to distribute this d to the x throughout addition and subtraction still. So this is the first derivative. We're done, right? The derivative of e to the x is e to the x. The derivative of x is just 1, and so e to the x minus 1. What if I want to find the second derivative? Second derivative is, well, that's the d dx of e to the x, if I want to kind of overkill it here, minus d dx of 1. The derivative of the constant is 0, right? So we have e to the x just kind of holds steady. Minus 0, putting me at e to the x. What's the third derivative? E to the x. What's the fourth derivative? E to the x. What's the fifth derivative? E to the x. Right, so on and so forth. Now that we've boiled down to just e to the x, it'll just stay e to the x forever, right? No matter how many derivatives you take. So you can compare the graphs. I can't remember if I put the graphs in the handout. No, I didn't. But how about this? We could talk about them. You can graph them and convince yourself that, okay, where I hit that minimum, that's where, and it's reflected in. So is there a reason that e to the x doesn't break down? No, it's just a special, it's special property. And so it makes it pretty useful too, is that the derivative is the same as the y value, so you'll always know what the derivative is and the slope of the tangent line. But yeah, it's just kind of like a cool property, which we don't see anywhere else. So just lock it in there. There's a lot to lock in today. Okay, so once we move into e to the x minus 5, for example, so if you have a function upstairs in the power, then things will change a little bit, right? So then we'll have something else going on. But we're not there quite yet. Yeah, but really good to keep an eye out for. So this is only for e to the x. Okay, good. Let's not compare the graphs. We've done enough comparing the graphs. I do want to finish that last example. So, I mean, feel free to compare the graph on your own, but there should be no surprises. Where the slope is negative, the graph of the derivative should be below the x-axis. Where the slope is 0, it should cross the x-axis, and where the slope is positive, it should be above the x-axis. All right. So let us expand our minds. At what point on the curve y equals e to the x is the tangent line parallel? Okay, so we have to remember what it means parallel. Well, two lines are parallel if they have the same slope, right? Just as a side note, if you need your lines to be perpendicular, remember that then the slope of the first line times slope of the second line has to equal -1. I'm going to summarize that here because that might come up. I don't know. I'm not foreshadowing or anything, but I suspect it might come up. So here, recall lines with slopes m1 and m2 are parallel if m1 is equal to m2, right? And so that's what we want in this case. And they're perpendicular, so 90-degree angles here. I think in the textbook, there's something called the normal line. So if you've got the tangent line, then the normal line is the line that's perpendicular to the tangent line at that point. So maybe I'll make a note of that as well. So they're perpendicular if you're able to show that m1 times m2 equals -1. And just as an additional note here, the normal line at a point is the line perpendicular to the tangent line at that point. So again, we have information about the slope and you have a point, so you can use that point slope form of the line. So the normal line. The normal line at a point is the line perpendicular to the tangent line at that point. So if we have something like, at the risk of looking like e to the x here, but here, if you have a tangent line, then this would be your normal line. Okay. So that's just some terminology, just in case I don't know we need it. Okay, so now that we've kind of gone back, reestablished what it means to be parallel and perpendicular, we can reread the question and just kind of figure out what we need to do. So at what point on the curve y equals e to the x is the tangent line parallel to the line y equals 2x? Now notice that y equals 2x, that's a straight line with a slope of 2 and a y-intercept of 0, right? And so I know the slope of this, of the second line, right? And I need the slope of the tangent line here to be 2, right? So we know y equals 2x is a straight line through 0, 0, right? Because the y-intercept is 0, with a slope of 2. So we need to find the point where the slope of the tangent line is 2. So we need to find the point where the slope of the tangent line is equal to 2. Well, that's the same as saying where the derivative is equal to 2, right? And so where y prime is equal to 2. Y from y equals e to the x, not y equals 2x. What's nice about y equals e to the x, well, the derivative of y equals e to the x is e to the x. So really what I need to force is e to the x being equal to 2. So if y equals e to the x, we know that y prime is also e to the x. Oops. So we need e to the x to be equal to 2, right? If we're forcing that derivative to be equal to 2 to have the same slope of y equals 2x. If I'm solving for x here, Well, I know to bring that x down from the power, I need to take the log, presumably the natural log, because that'll cancel out the e. So here, I'm going to take the natural log of e to the x, but I have to do it to both sides, is the natural log of 2. But when I take the natural log of e to the x, it just drops out to x, right? And that's how I'm able to bring that power downstairs. Technically, what's going on is this x is being brought down in front, right? So it's been a long time since we dealt with logs. But just remember, if you take the log of e to the x, you just get x. And the log of 2 is just some number. It's just going to be a nasty decimal, probably. So x becomes the log of 2. I'm going to keep it as in the exact form. Okay, womp womp, there it is. I found the value of x that makes the slope be 2 for the tangent line. At x equals the log of 2, I can find the y value, and it should be 2 because we know we've got the inside scoop on e to the x, but we can just confirm at x equals 2, we find that y equals e to the x. Well, y equals e to the x is y equals e to the log of x. Sorry, log of 2. Is x. That's what confused me. I think x is the log of 2, not just 2. Well, e to the log of 2 is just 2, so y equals 2. And you can reword the question as an answer, but I'm just going to do it quickly here. So the point is at the log of 2 and 2. Right. Okay. So before I let you go, I just want to introduce the product and the quotient rule, just so you have a little bit of time to think about it. Right, we're not going to do any examples or anything, but just so we introduce them. So 3.2 is the product and quotient rules. So just to introduce them, so we've seen them once, not to use or anything. If you have the product or the quotient, we can't just take the derivatives of the products and multiply the derivatives together, because that's not going to work. Okay, so products and quotients are division, right? So quotient rules is for division. Okay. So if you're multiplying or dividing, then we have these different rules. And from the handouts, you'll see that they've used the ddx notation, blah, blah, blah. For us, I actually like to rewrite. They've got the prime notation in a slightly different order, but I like to use the same order for both of these. So I'll show you what I mean. So the product rule just in kind of prime notation. So now I've got f and g, which are two differentiable functions, and they're being multiplied together. If I have to take the derivative of this, what we have to do is this becomes the derivative of f times g, right, plus f times the derivative of g. And that's going to take a little bit of practice, right, to recognize that two functions are being multiplied together. That can take some practice to see, right? Okay, I've got two functions being multiplied. I need the product rule, but also applying it. And so kind of in the same breath, we've got the quotient rule, which says that if you have f over g, right, so a function over a function, and you want to take the derivative of that, this one's probably the nastiest, is it becomes f prime g minus f g prime. So notice that I use the same setup for each of these, which the textbook doesn't. Notice that this is subtracting instead of adding, right? But these two kind of translate down, and that's what I wanted to highlight. And then just kind of weird out of nowhere, we get, well, not out of nowhere, over g squared, which is the original function of g squared. And I think that's just enough to confuse you for the weekend. What do you think? I know. So we're going to use the product and quotient rules next day, but I just wanted you to see them, know that they're weird, and we're just going to work through them. And we'll use them some more. Maybe also have a sneak peek at section 3.3, the 3.3 notes. It's really just the derivatives of trig functions. We just need to memorize those. And by memorize, I mean have those derivatives somewhere available close by, because obviously everything is open book. So for you, you don't have to memorize them. If we were in person, you'd have to memorize them. So you can just be happy about that.
Sometimes. All right. I'm going to see if about doing that brain cell scraping and then getting the test and stuff done.
I know. Maybe have some lunch or something first.
Yeah. Probably a good idea. Maybe a 15-minute nap. We'll see. Anyways, ta-ta. See you Tuesday.
All right. See ya.